then we denote the determinant of A by det of A or by this symbol. So either of this will stand for determinant of a matrix. Now determinant of a matrix is a number associated with that matrix. Which number exactly is associated is a different story, but one can think of determinants as being a function from the set of all square matrices to the set of real numbers. In other words, determinant of a matrix is nothing but a number associated with the matrix. Now, as I was mentioning, what exactly is that number is an entirely different story, and that will take us into realms of pure mathematics. There are several ways of defining the determinant of a matrix. One of which is using permutations, elementary products, signed elementary products, and so on. Another method is to define it recursively. That means I will define the determinant of a matrix of order n minus 1 and use it to define the determinant of a matrix of order n. And there are several other ways. One is the axiomatic way of defining the determinant, but I am not going to get into any of these definitions because just to be able to define the determinant of a matrix properly, it should take a minimum of half an hour. And it's not really worth the effort because of the amount of portion that is there. So it is enough for me, rather it serves my purpose if you have at least some idea of what is determinant of a matrix and you know at least one method of evaluating the determinant of a matrix. So assuming that you already have some idea of what is determinant, we will go further. A matrix is said to be a matrix A, a square matrix A, is said to be non-singular if and only if the determinant of that matrix is not 0. So a matrix is said to be non-singular if and only if the determinant is not 0. Otherwise, we say that it is a singular matrix. So for a singular matrix, the determinant will have to be equal to 0. And as I was mentioning in the last lecture, the question of whether a matrix has an inverse or no is closely related with the determinant. Let me mention that once again over here. A square matrix A is invertible if and only if A is non-singular. So a square matrix will be invertible, that means it will have an inverse if and only if it is non-singular, that is if and only if the determinant is not equal to 0. So if I take the matrix A to be 1, 3, 1, 3, then the determinant of this matrix is product of the diagonals minus product of the non-diagonal elements. This is 0. So this happens to be a singular matrix, and that's why this matrix is not invertible. So at least this way, by computing the determinant of a matrix, one can determine whether the matrix has an inverse or does not have an inverse. Well, after you know that a matrix has an inverse, how to calculate the inverse is a different story again. And we'll tackle that problem at a slightly later stage. So I'll come back to this question of how to find the inverse of a matrix a little later. Let's continue with the determinants. What we are now going to do is give an alternate method of finding the determinant of a matrix. So for that, I need to introduce the concept of minors and cofactors. So let's again start with a square matrix. Let A equal to Aij be a square matrix of order n. The minor of the element Aij denoted by capital Mij and is the determinant of the submatrix and is the determinant of the submatrix obtained by deleting the I row and j column of capital. It will be easier to explain this definition if I take an example. But while we are at this, let me quickly again explain what we mean by minor of an element Aij. Suppose I am calculating the minor capital Mij, then what I need to do is from the matrix A, delete the ith row, j column. We will be left with a matrix of order n minus 1 because there will be 1 row and 1 column less. Take the determinant of that submatrix, that will give us the minor. And the cofactor of this element, the cofactor of Aij is denoted by Cij and is defined to be minus 1 raised to I plus j times Mij. So you notice that the cofactor is not too different from the minor in the sense it is the minor with the appropriate sign plus or minus. Now this is minus 1 raised to some power. So and we know that minus 1 raised to an even power is plus 1. Minus 1 raised to an odd power is minus 1. So it is very clear that the cofactor will be equal to the minor if I plus j is even, because then minus 1 raised to an even number will be plus 1. So Cij will be equal to Mij. And if I plus j is odd, then this is minus 1 raised to an odd number, that will give us minus 1. So in that case, Cij will be minus Mij if I plus j is odd. So cofactor is either equal to the minor or it is negative of the minor depending on whether I plus j is even or odd. As I said, it's much easier to understand the definition if we look at an example. So let's take a 3 by 3 matrix and try and calculate the minor and the cofactor of every element in that matrix. So let us take A to B. 1, 3, minus 2, 0, 4, 5, 3, 1, 4. There are 9 elements in all. So for each element, let me calculate the minor and the corresponding cofactor. Let us start with the minor of the element in the first row, first column. Remember what the definition says. To calculate the minor of the element in the first row, first column, delete the first row and the first column. Take the determinant of the remaining submatrix. So for the minor of the element in the first row, first column, remove the first row, first column, see what is remaining, take the determinant of this remaining submatrix. That works out to be 4 into 4, 16, minus 1 into 5, that is 11. And notice that 1 plus 1 is even. So cofactor will be equal to the minor and therefore this cofactor will have to be 11. Next, let's obtain the minor of the element in the first row, second column. Now we have to delete the first row and the second column. So if we do that, the remaining submatrix is 0, 5, 3, 4. Determinant of this matrix will be 0 minus 15, that is minus 15, and 1 plus 2 is odd. So cofactor will be minus negative of the minor. Minor itself is minus 15. So cofactor will be the negative of this and therefore cofactor will be plus 15. next element in the first row, third column, and let's calculate its minor. Now we need to delete the first row and the third column so that we have determinant of 0, 4, 3, 1. That will be 0 minus 12, that is minus 12, and 1 plus 3 is even. So cofactor will be equal to the minor, and therefore cofactor will be minus 12. We are done with the minors and the cofactors of the elements from the first row. Now let's move on to the second row. Let's calculate the minor of the element in the second row, first column. Now, for this element, second row, first column, we have to delete the second row and the first column. So we are left with determinant of 3 minus 2, 1, 4. 3 4s are 12. Minus of minus 2, that's 14. 2 plus 1 is odd. So C21 will be negative of this minor, and that will be equal to minus 14. Similarly, when I take the minor of the element in the second row, second column, I'll have to delete the second row, second column. If you do that, you'll be left with determinant of 1 minus 2, 3, 4, which is equal to 4 plus 12, 16. And cofactor will be equal to the minor because the sum is even. Then we go to the element in the second row, third column. So delete the second row and the third column. We'll have 1, 3, 3, 1. 1 minus 9 is minus 8. And this time 2 plus 3 is odd. So cofactor will be the negative of this. Therefore cofactor will be equal to 8. Then let us go to elements in the third row and find their minors and cofactors. So let's start with the element in the third row, first column. So delete the third row and the first column. That leaves us with this submatrix. Take the determinant of this 3 minus 2, 4, 5. 3 5s are 15 plus 8, that is 23, and C31 will be 23. Then N32 this time, leave out the third row and second column. Leave out the third row and the second column. So we get 1 minus 2, 0, 5. So that will be 5. And C32 will be equal to minus 5. Because the sum is odd now. Sum of the suffixes. And then finally we come to the last element, N33. Leave out third row, third column, so we get 1, 3, 0, 4. You get 4 minus 0, that's 4. C33 will be equal to 4. So this is how we get the minors and the cofactors of all the elements of the matrix. Now here's a very interesting observation. Let me first write down the elements of this matrix. Notice that for this matrix, A11 is 1, A12 is 3. I am writing the elements of the matrix. A13 is minus 2, A21 is 0, A22 is 4, A23 is 5. Then elements in the third row, first column, 3, third row, second column, 1, and third row, third column is 4. The reason why I have listed all this is that if we now calculate this expression, see I take elements from the first row. Let me take elements from the first row. So I have A11, A12, A13. Let me take the corresponding cofactors and multiply it. So C11, C12, C13. Multiply the elements of a particular row with the corresponding cofactors and let us add all such terms. So A11 is 1, A11 is 1 into C11. C11 is 11 plus A12 is 3. C12 is 15, A13 is minus 2 and C13 is minus 12. So if I simplify this, I'll get 11 plus 45 plus 24, which is going to work out to be 8. I don't believe it will be 80. So this sum works out to be 80. Let us see what happens if I use elements of the second row, multiply them with the corresponding cofactors. So I am taking elements from the second row, multiply by the corresponding cofactors, and then I am going to add all such products. A21. If you have the matrix with you, you can see it from there. If not, I have listed the elements over here. A21 is 0, A22 is 4, A23 is 5. So I have 0, 4, 5. 0, 4, 5. And cofactors C21, C22, C23, they are minus 14, 16 and 8. So this will be 0. This will be 64. This is 32. This again turns out to be 80. Similarly, let me assure you that if I take elements from the third row, multiply them with the corresponding cofactors, you will once again get this sum to be 80. So, if I take elements from a particular row, multiply by the corresponding cofactors and add all such terms, I get a constant. And there is a result which I am not going to be proving, but this constant number turns out to be the determinant of the matrix. So this gives us a method for evaluating the determinant of a matrix. So I'll give this as a definition. Let capital A equal to Aij be a square matrix of order n. Then, if you take elements from any particular row, in general, let me take the elements of the ith row. So, if I take elements of the ith row, multiply them with the corresponding cofactors. If I take elements of the ith row, multiply with the corresponding cofactors and add all such products, I get the determinant of the matrix. This method of evaluating the determinant is called the cofactor expansion. It's called the cofactor expansion of determinant of A along the ith row. So this is a method of evaluating the determinant, and this is using cofactors. That's why it's called the cofactor expansion. And since we have used elements and cofactors of the ith row, this is called cofactor expansion along the ith row. Now I can be anything. You can use first row, second row, third row, whichever one is convenient. And there's absolutely no reason to be partial to the rows. The same story works even if you use a particular column. So, if I happen to use the jth column of the matrix, so I need elements from the jth column. Keep in mind that the first suffix denotes the row number. That's why when I mentioned I am taking elements of the ith row, throughout my first suffix was I. And second suffix stands for the column number. So when I say that I want elements from the jth column, throughout my second suffix is going to be j. So look at the expression A1j, C1j, A2j, C2j, ANJ, CNJ. You can bet on it that this also will work out to be the determinant of A. And this formula is called the cofactor expansion of determinant of A along the jth column. So depending on your problem and your convenience, you can evaluate the determinant either along a particular row or any of the columns. So let's look at one or two problems on this. Let us evaluate determinant of A by cofactor expansion along the second row. A is given to be the matrix 3 minus 1 2 6 2 4 0 2 1. So we've been asked to evaluate the determinant by cofactor expansion using the elements of the second row. So let me first write down the formula. I need to use elements of the second row. Elements of the second row will be denoted by A21, A22, A23, because this is a matrix with 3 rows and 3 columns. The elements in the second row will be A21, A22, A23. Multiply the elements with the corresponding cofactors and then add all such products. So this is going to be the formula for determinant of A along the second row. Now let me evaluate these 3 cofactors. Remember, for the cofactors, I first need to know what are the minors. And then once I put the appropriate sign for the minor, I get the cofactor. So let's start with the minor of the element A21. For the minor of the element in the second row first column, I need to delete the second row first column and take the determinant of the remaining submatrix. So it will be minus 1 minus 4, that is minus 5, 2 plus 1 is odd. So cofactor will be negative of the minor. Minor itself is minus 5, so cofactor will be plus 5. Then look at M22. Now here the second row, second column. So we have 3, 2, 0, 1. Determinant of this is 3 minus 0, that is 3. 2 plus 2 is even. So cofactor will be equal to this minor. So cofactor is 3. Then M23. Leave out the second row. Leave out the second row and the third column. So that gives us 3 minus 1, 0, 2. That is 6. And C23 will be minus 6. Also, if you look at the elements in the second row, look at the elements of the matrix in the second row. A21 is 6, A22 is 2, A23 is 4. And now all one has to do is substitute in this equation. So we will get determinant of A. So determinant of A is 6 into 5 plus 2 into 3 plus 4 into minus 6. This will work out to be 30 plus 6 minus 24. 30 minus 24 is 6, 6 plus 6 is 12. So determinant of this matrix is 12. If in the problem the choice is given to us, then we have no option but to go by that particular row or that particular column. However, if we've been asked to evaluate the determinant by simply cofactor expansion and no particular row or column is mentioned, then the choice is entirely up to us. At such a time, maximum number of zeros. That way you will end up doing least number of calculations. So let's look at one more problem. Let A equal to 310 minus 2 minus 4 3 5 4 minus 2. Evaluate determinant of A by cofactor expansion. And this time let's not mention any row or any column. So since the choice is left to us, I noticed that there is one zero in the matrix. So either I should find the cofactor expansion by the first row or by the third column. This time I will go in for cofactor expansion along a column, because in the earlier problem we had done cofactor expansion along a row. So you have absolute freedom to use any one of the three rows, any one of the three columns. But if you want to minimize your effort, then go for a row or a column which contains one or more than one zeros, maximum number of zeros. So either the first row or the third row should be advisable in this problem. I'll go for the third column. So if I use cofactor expansion along the third column, I'll get determinant of A to be A13, C13, A23, C23, A33, C33. Now A13 is 0, A23 is 3 and A33 is minus 2. Notice that since A13 is 0, 0 into any other number is going to be 0. So there is absolutely no need to calculate C13, because this product is going to become 0. So it is enough to calculate C23 and C33. So let's do that. So let us first get the minor of the element in the second row, third column. So we need M23. Now here leave out the second row and the third column. So we will have determinant of 3, 1, 5, 4. That's 12 minus 5. 12 minus 5 is 7. 2 plus 3 is odd. So C23 will be minus of that minor. That means C23 will be minus 7. M33. Now leave out the third row, third column. So we have 3, 1. Leave out the third row and the third column. That leaves us with this submatrix 3, 1, minus 2, minus 4. That is minus 12 plus 2, which is minus 10. And therefore C33. 3 plus 3 is even, so this will be minus 10. And now let us substitute in equation 1. So determinant of A is, as I had mentioned, the first product is 0. Then we have A23, which is 3, into C23, which is minus 7, plus A33, that is minus 2, into C33, that is minus 10. So this works out to be minus 21 plus 20, which is equal to minus 1. So this is one very efficient method of evaluating the determinant of a matrix. Of course, a better method